Okay, good morning, good evening, wherever you are. Welcome to our webinar from Hydronia. We'll be talking today about tailings dam modeling. And just before getting started, if you can give me a quick note on the chat window or on the question panel, if you can hear me well, just to make sure that sound is working properly, that would be great. Okay, it seems that you can hear me well. Okay, so let's get started. Just a brief mention that the webinar is being recorded, and that after the webinar, the recording is processed and you will get an email indicating the instructions to watch it. And if you have to leave for any reason, or if you want to share that link with your colleagues, you're free to do it. There is no cost involved in that. And that will allow you to watch the webinar later. Okay, so let's get started. Today's webinar title is Tailings Dam Break Flood Modeling, Unique Capabilities That You Probably Didn't Know About RiverFlow2D MT. So the webinar is, we decided to do this webinar based on several questions that we get from people interested in our tool, but also from users that are using the RiverFlow2D MT model, but sometimes they are not aware of many of the features that get developed for the model. And that's probably because we are adding new features on a frequent base. So we get to add things that sometimes if you're used to one capability, maybe you're not exploring some others, and that's the purpose. So the idea is that I will be going over some of these questions and trying to answer them. If you have further things to ask, for sure, please feel free to ask them at the end or using your question panel. So first, for those of you who are not familiar with RiverFlow2D, I will briefly tell you what is RiverFlow2D MT. Then some of the frequent questions that we get is, can the model simulate dam breaks of dry deposits, of dry tailings? It is possible to consider different material properties for the dam different from those of the deposit. It is feasible to have water reservoirs and model how the water mix with tailings that may arrive to or flow into the reservoir. Can the model include water tributaries, and also how these water tributaries mix with the tailings? It is possible to include rainfall, and if the rainfall affect in any way the material concentration of the deposit or the flowing tailings. Could the model simulate pollutants together with tailings flow? Is the model able to calculate dam breach by erosion of the dam that contains the tailings? So these are the questions we are going to address today. So the first one is, what is RiverFlow2D MT? So RiverFlow2D, in a nutshell, is a two-dimensional hydrologic flexible mesh model that can simulate the flow of water and non-Newtonian fluids or mixtures of them It's in a way a two-phase model that uses the shallow water equations or a kind of shallow water equations for the material and the water flow, and solves those equations with a finite volume numerical engine. And I stress this because the advantage of the finite volume numerical engine, besides the high stability and the speed that it can achieve while solving the equations, is that it ensures complete and exact volume and mass conservation, which is essential to simulate tailings dams. You can add to your model environment hydraulic structures such as culverts, weirs, bridges, gates, bridges, covers, and dam breaches. It works in English and metric units. So if you live in a country that uses metric units, like 99% of the world, then you can use that. If you live in a country that uses English units, then you can also use exactly the same tools to work in that measuring system. The user interface is based on QGIS, which is an open source software, and it is free as well. So the graphical user interface of RiverFlow2D is of free distribution. So Hadronia doesn't charge for the graphical user interface. So what you're actually getting, if you get a license, what you're getting is an engine that is, of course, you will get QGIS and the integration with the GUI, but the advantage is that you can install the GUI in multiple computers, and with a single license, you only need the license to run the model, but all the development time for your simulation, preparing the simulation, generating meshes, and so forth, and also post-processing can be done in any computer and in multiple computers at the same time. The model can do with the GUI hydraulic and hazard maps, and also animations. And we have recently added the option to calculate or develop maps for damage cost. So if you have vulnerability cost functions for different areas, then you can develop these maps that tell you how much would a flooding cost in depending on those functions and in the hydraulic conditions that the flooding creates. The model has a GPU option that which means that it can run much faster if you have the proper NVIDIA GPU card, and that allows it to run significantly faster than other tools that you may find around. The specific module I'm referring to today is the MT module, the modern debris flows and tailing dams is the MT. But the model also has options to modules for other applications like sediment transport, urban drainage, pollutant transport, and water quality. The main characteristics of the model is the flexible mesh. You already know that probably. So the mesh is formed by triangles where all the action is occurring. So the computational unit is the triangle, and those triangles can have any size and can be adapted to any geometry. Now the MT is a comprehensive two-phase model that deals with water and also the solid material separately. So we can handle track the characteristics of the solid flow and also the water flow separately. The mixture can be non-Newtonian, which means that it can via variable viscosity and variable yield stress. The bottom material size can vary in space, and surely in a new forthcoming version that we are going to release in the coming month, it can also vary in time. So the properties of the active layer not only will change in space, but will also change in time due to the interaction with the flowing material. The inflows can have different sediment characteristics and concentrations. The fluid within the mesh can have different solid concentrations and properties. The fluid properties can vary in space and time also, not only what is in the bed, and it can do erosion and deposition. So the bed is not a fixed bed. It can erode, and you can have sedimentation and deposition as well. A non-erodible layer can exist below the erodible bottom, or you can have a paved surface of a road that cannot erode, and you can simulate those also in the model. Rainfall interacts with the flowing mixture, so you can add that feature as well. So next question: can the model simulate flow of dry deposit? There are many deposits that contain a lot of water. Those are wet deposits, normally called. There are deposits that are totally dry. They do not behave in the same way as the lubricated or the materials, the deposits that contain a lot of water. So how can this be handled in RiverFlow2D MT? So RiverFlow2D MT is a non-Newtonian flow model that can handle a wide range of different materials and how they flow. And this is done in part by the use of multiple rheological formulations that are available in the model that you can select from. So these are the 9 options that you get when you model with the MT model. So you have turbulent mixing, turbulent manning option, which is an option that essentially represents the flow of water or Newtonian fluid. So it's a standard water flow model. So you have that option. Then you have the Bingham models, the 2 Bingham model. One is with the full cubic equations typical of the Bingham model that is applicable mostly for cohesive viscoplastic materials like type of paste with high concentrations of fines, and also the Bingham simplified Bingham, which is a subset or a simplified version of the full Bingham, where you don't need to solve the cubic equations, and gives similar results in many cases. Then we have the turbulent Coulomb and also the turbulent Coulomb and yield, which include the frictional components for materials that are so, you have the solid phase that is so close together that the friction between the solid grains becomes very, very important. And these 2 types of rheological formulations are very useful for those type of flows. Now, one thing that happens in these flows is that when you have low volume concentrations, you cannot use exactly the same formulations, because when you have low flow, low concentrations of the solid material, the fluid behaves as a turbulent flow, and that's why it's called the turbulent Coulomb or turbulent Coulomb and yield. And in this case, when you have concentrations below approximately 15%, then the flow behaves as standard Newtonian fluid. And when the concentrations of the material is above 15%, then the material behaves as a turbulent Coulomb or turbulent Coulomb yield rheological formulation. And we have the quadratic, which is similar to one applied in other models. Some models include only this one here, or something similar to this that includes Manning, friction, and yield stress, and also some internal friction due to viscosity. But then we have also the granular, which is one that applies to a purely frictional material where you don't have necessarily any water content. And this is the one that you may want to use for the dry stack. We also have added recently the Herschel-Buckley model, which is quite popular in some applications where you have also the high concentrations of viscous or fine material that create a viscous, very viscous flow. So you have all these options, and particularly the granular will be the one for the dry stack. So in addition to using the dry granular formulation for dry stacks, I wanted to mention that we have added recently the Landslide tool. The Landslide tool that also will be available in the version 8.05. It's a way to simplify the input of the initial landslide location. So what you do is you create the new or generate the new landslides layer in QGIS, then enter a polygon. And when you enter the polygon, you have the option to select the depth of this landslide. That will be the initial depth of the landslide. Or you can enter a volume. If you enter the depth, the model will compute the volume. Or if you enter the volume, the model will compute the depth. And you can also enter the initial concentrations of the different classes that I will talk about corresponding to this volume. So once you enter that will be your initial conditions. From the DEM, the digital elevation model that you may have entered here, the model will subtract that volume, and that will be your initial volume that will start moving according to the properties that you assign to that landslide. So it's a little simple tool that you can use to enter your landslide data. Okay, so let's move on. Next question is it possible to consider different material properties for the dam and its deposit? So this thing is this: you have a dam or an initial location of the dam, and behind the dam you have a deposit, but both have different properties. They have different soil, they have different materials, and oftentimes you need to consider the different properties of that dam materials with respect to the ones you have in the deposit that may be dry or wet or whatever you have. So for that, you need to understand the concept of sediment classes. In RiverFlow2D, you can model the material with multiple classes of sediment or multiple types of sediment. So a class is defined by different types of sediment or solid material and can represent different materials for the terrain, the deposit, or the flowing material as well. The classes are identified by their properties, the characteristic diameter, the density or weight per unit volume of the material, and the critical stress for incipient motion. So by adding data for these classes, you can incorporate many different types of materials. For instance, here you see we have a class that has a density of 2,700 kilograms per cubic meter, and you have a class that you can easily identify here as an iron that has a density of 7,874 kilograms per cubic meter. So these are classes that may be present or not in different areas, as we will see. So you can have different concentrations of each class in the flowing material. You can have different percentages or fractions in the active layer, and you can have different classes coming in from inflow tributaries or from existing ponds, as we will see. So the class is a key concept that we added to the model so that you can mix and match different materials, not only existing as initial conditions, but also in the terrain and in the coming tributaries that you may have in your application. So in particularly when you want to set different properties or type of material to the dam than to the deposit, what you do is you create in the initial concentration layer in the RiverFlow2D QGIS interface, you enter a polygon that represents your dam. So this will be the dam here, and you may recognize this is the dam that failed near Brumadinho in Brazil a few years back. And this is the deposit. So the deposit here has a property characterized by the classes, and the classes have different concentrations. And then you have the classes within the dam that will have some of them 0 because they are not do not exist within the material that form the dam itself or the dams. So in this way, you can consider different materials for different areas within your simulation. Okay, so let's move on to next slide. Next question is, it is feasible to include water reservoir and model the water mixing with tailings? Well, this question is related to the previous one, because in the same way that you can have different material properties with different concentrations, you can also have a water reservoir. And in this case, just to illustrate the issue, even though there was no actually reservoir here in the Brumadinho failure, I have added here a water reservoir downstream from the actual tailings deposit and dam. And in this case, this water reservoir contains 0 concentrations of the classes. So what this means is that this is a water reservoir, and whatever volume is represented here that can be added with initial water surface elevation, separate from the initial raster that is set here. So you can have initial water conditions here and an initial deposit here. And when the flow start occurring from the dam, will mix with the reservoir, the water reservoir here, and the properties will change and will mix according to the flow solution that is obtained by the equations. So yes, you can have a water reservoir or many water reservoirs that can mix with the incoming flow from the tailings. You can have also the water reservoir upstream and failings from the water will mix with the tailings downstream if that is something that you have in your application. Next question is, can the model consider water tributaries and their mixing with tailings? So sometimes you have the tailings that arrive to a river that is a flowing river, and that you need to see how that affects the river flow. So the answer is yes, you can have a river. In this case, again, it's an example of the Brumadinho case. So you have the Paraopeba River that is flowing in this direction downstream, and then we are modeling the tailings flow coming from the dam. And then you can model all the mixing, the damming of the rivering conditions, and also the erosion and deposition that can be occurring here according to the arrival of the tailings into the existing flowing river. So what you see here is the concentrations of the mixture, and as you saw initially, you have the high concentrations of the tailings, but then the water eventually takes over and it starts eroding the material and moving it downstream. Okay, next question is it possible to include rainfall and its effects on the material concentrations? Well, yes. The rainfall and infiltration, although infiltration is not so critical in many tailings applications, but you can also include it if you want. But the rainfall and infiltration can be added in a spatially distributed manner, of course, in a time variation manner. So you can add a storm only upstream from in the watershed or downstream or in any location, or you can have a variable rainfall distribution that can affect the area in different ways. And as the rainfall enters your mesh, it will mix with the material that exists or is flowing, and it will modify its concentration. And by modifying the concentration, eventually, of course, we'll modify the density, viscosity, and yield stress. So the rainfall may alter in a big way an event. If you had an event occurring during a rainfall situation, then you can have that as an S scenario and model that as well. So next question is, can the model simulate pollutants present in deposits together with the tailings flow? So this is something that many users are not aware of, but in addition to model the actual flow of the solid material, you can add one of the classes that you add in the model can be a pollutant. It can be one of the components of the deposit, can be a metal, or it can be any other material as well. So that means that you can have a certain concentration of the pollutant within the dam, and while you are modeling, or the model is computing the flow of that solid material, it also simulates the concentration of the pollutant that you have in the dam. And this is an example of a initial concentration of the pollutant that is moving downstream, and you see it here as that is being washed out also by the flowing water of the Paraopeba River here. So it's just an example, and then you get at the end the accumulation concentration of the material close to the dam, and then the lower concentrations that were washed away by the water component. So you get two things. You get to model the actual material flow, but also the the concentration of the pollutant. So it's something that you may want to consider when applying the model as well. Okay, I guess this is our last question for today. Is the model able to calculate dam breach by erosion? We had a webinar a few weeks back about this tool. And yes, you can model dam breach component using 3 failure modes. They prescribed, where you define in a initial way how the breach will form in time, you know, when the model starts running, you already know how the dam will fail. But you can also model it dynamically by using the overtopping or piping modes. And in this way, the model can actually model the erosion of the dam and how that erosion will create a discharge hydrograph through the dam. So that's something that the model can do as well. And that's it. I want to know if you have any other question. So if you have any questions, you're free to use the question panel. And I see I have a few questions already, so let me read them and try to answer them in order. Okay, so first question is, can the RiverFlow2D model simulate multiple dam breaks that occur at different times? Well, incidentally, this was there is an application going on by a good user we have in Japan that they are modeling multiple. They want to model multiple dams that they do not occur simultaneously. Okay, yes, the answer is yes. You can model multiple dam breaks that occur at different times. And if you were to use the initial conditions only, then the dams would fail at the same time. But if you use the dam breach component together with the initial conditions that represents the dam height and conditions, then you can set the dam breaches to start at different times. And in doing so, your dams will fail not simultaneously, but according to the times that you select in your dam breach models. So the dam breach, in the dam breach component, you select the time at which the dam breach component will start. That doesn't mean that the erosion will suddenly occur, but it will start eroding the dam at the time that you select. So yes, the answer would be yes in that case. Second question, can the model consider variable bed granulometry and its evolution in time? For example, bed armoring. Well, in the version that we are releasing in the next month or so, 8.05, that version 8.05 will include the active layer. And let me see if I can show it to you. Let's see, try to see if I can show you this. In the 8.05 version, you will have this option here that says bed fraction evolution. With this option, you will be able to simulate how the bed granulometry changes in time and space as well. So based on the interaction with the flowing material, the the granulometry can get coarser or finer depending on the active layer interaction. So that's what we have. And now that I show this, I remember that you can also, you know, we offer a number, the way that the model responds to the changes in volume concentration. As the model computes the density and the volume concentration, you have three options to consider how that volume concentration affects the viscosity and the yield stress. And so you have the option to select a formula, but the problem with these formulas sometimes is that they are not applicable to your case, and you have data. So we have users that collect and gather the data and do lab experimentations where they generate a table, and the table tells you the viscosity or yield stress for each volume concentration. And with this option, then you have the way to enter a specific table that tells you how that viscosity or the yield stress will vary with the volume concentration. That is very important because there are many cases where you have the actual data and there is no formula from this that is applicable to your case. So I wanted to mention that in passing as well. Okay, so that's that question. So let me go to next question. How can we simulate the collapse of a dry deposit like dam break that falls into a water reservoir? How can we apply different rheological properties, granular flow for the dry deposits and water for the reservoir in the same simulation? Okay, what the model does is that when the concentration, if you define, let me see, let me show this here. Let me go back to this here. Okay, if you define different, let's say this is a dry deposit, and then you have here a water deposit, right? So when the concentration of the material falls below 15% approximately, then the equations that are used or the rheological formulation that will be used for those low concentrations that can be zero will be those of turbulent flow, while those for the high concentration fluid will be of the rheological formulations that you have selected, let's say the Coulomb formulations or dry. So that's how the model deals with different conditions that can be in different areas of the flow. Okay, next question is, what parameters do you use to calibrate the rainfall runoff model? Okay, in rainfall runoff, you can use the Manning's equation. Normally, the way the model considers the rainfall runoff process is nothing different from your flow model. So what happens is that you have a rainfall event, and then the rainfall enters your mesh, let's say one cell. That it's a volume added in that specific time step to the let's say the point where the rainfall occurs. So let me come here to here. So if you have a rainfall event then eventually, let's say you are applying a rainfall to this area, and at some point the rainfall volume enters one cell. That cell, once the volume enters the cell, then the flow will occur. The runoff will depend on how the equations deal with that in a cell-to-cell basis. So Manning's roughness coefficient will determine how fast that that flow occurs in one condition. But also, since in the MT model the rain's mixed with the flowing material that can be highly viscous, so you can use other parameters that refer to the settling velocity factor, for instance, and other factors that you may tweak in order to calibrate the model as well. So in the model data, so depending on the equations that you select from here, for instance, then you have other factors that you may play with, like settling velocity factor. So the settling velocity, the lower the factor, the less sedimentation will occur. So you can use that. But normally in a rainfall runoff or purely rainfall runoff water flow, you use the Manning's equation, and of course, if the Manning's n, or if you are using infiltration, then you can also use the hydraulic conductivity of the terrain, or the Kerr number, if you use that for the particular infiltration formula. So those are the two that you may want to check. Next question is, in the piping mode, how does the program calculate the advance of the breach? Well, I didn't enter in the detail of that because we had a webinar a few weeks back that details that, but you can refer to that webinar. There is a video of the complete webinar, but just briefly, let me see if I can if I have it just to okay, let me see if I can show you this very quickly. I don't want to go into the details, but I will provide that that link to you. But in the piping breach, we consider a idealized geometry of the piping that can expand in time, and eventually that pipe geometry or orifice can collapse and form like a trapezoidal overtopping here. And that is it's a dynamic process. There are equations that determine the vertical erosion rate, the horizontal erosion rates, and at some point, critical point, this collapses, and then the model computes the hydrograph that dynamically within the mesh of the piping. So the details, I can provide that to you. And it's all in that webinar that we gave a few weeks back. The landslides are already available in the current version of RiverFlow2D. No, will be current version is 8.04. The next version will have that tool, is version 8.05, and will probably be released in a couple of weeks at most, because it's under testing, final testing stage. I have a question here. It's not a question, it's a comment. Congratulations, RiverFlow2D has become a monster. I hope it's a good monster. Is the model able to simulate open dams like silt or window dams for sediment control in mountain rivers? Yes, it can. It can do that too. You can enter the specific geometry of an open or partially open dam, and with bands that can block the flow, and some portions that can let the coarser material pass, and you can model that too, because the flexible mesh allows you to enter those obstacles quite easily. Okay, yes, Elias. Yes, Elias, I will send you that that link. Okay, let's get to, I guess, is the final question for today. If I got it right, the model would switch the rheological model automatically according to the CV. For instance, if set to granular model as initial condition and the dry material run into water reservoir, so the model will account for the total volume as a mud flow or even water flow. Yes, that is correct. You understood it correctly. The model switches according to, especially switches when you have low concentrations for the turbulent type of material. Yes. Okay, so I guess that's our last question. I just need to thank you very much. Quite interesting questions. Many of this will be included in future webinars for the benefits of all. And if you have any comment, or if you want to ask, you know, for specific things you want to see in the model that we don't have now, we are open all the time to add new features. By the way, many of the features that you see in the model now are a product of requests that we get from users. So we try to improve the model all the time, and we are open for those suggestions. So thank you very much, and I'll see you in coming webinar. Okay, bye-bye.